what packing fraction is. Packing fraction is nothing but the ratio of difference between atomic mass m of an atom and its mass number a to its mass number. This you can simply write it as, this is a ratio of difference between the mass, atomic mass, that is m, of an atom and its mass number. So difference between atomic mass m and mass number to its mass number. So packing fraction is the ratio of difference between the atomic mass m of an atom and its mass number a to its mass number. So if you have atoms with the negative packing fraction, they are more stable, and atoms with positive packing fraction are less stable. So I think you understood everything now. So we have seen the binding energy, specific binding energy, and packing fraction. So I think you have no doubts. If you have any doubts, you can clarify. Now let us study about binding energy curve. So what a binding energy curve is that? So a graphical representation of variation of binding energy per nucleon with the mass number of nuclei of atoms of different elements is nothing but the binding energy curve. That is, it's my rough diagram. So it's a graphical representation of variation of binding energy per nucleon with mass number of nuclei of atoms of different number. Okay, this is in mega electron volt. So students, a binding energy curve is nothing but it is a graphical representation. Graphical representation of variation of binding energy per nucleon with mass number of nuclei of the different elements. So that is nothing but binding energy curve. Now there are some features of binding energy curve. Let us see some features related to binding energy curve. So it goes like this. Go to the textbook so that you can get a good image rather than mine. It's a rough sketch, okay? So let us see some of the features of the binding energy curve. Binding energy curve, there are like this. So student, it's my rough sketch as I told. Be sure to go to the textbook so that there will be no confusions. So it is insufficient, okay? Don't laugh at my picture. Gen 14, O16 and O18, that is oxygen. Sulfur 32, ferrous 56, molybdenum 100, and iodine 127, 984, 197, and uranium 238. Okay, this is my rough sketch. So let us see the features of binding energy curve. So features, the binding energy per nucleon, that is ABN, is practically independent of atomic number, right? It is independent of atomic number, that is constant for nuclei of middle classes from 30, okay, from here to 30 to 170. So till here it is nearly constant. For these elements it is constant. Therefore binding energy binding energy per nucleon is independent of atomic number. This is mass number. You should take care of it. Don't get confused. Therefore, which implies that it is constant for nuclei of middle class from here to 170, nearly here. Okay, you go through the textbook so that you can understand this part. And second feature is that the curve has a maximum value of about 8.75 mega electron volt for mass number 56 and 7.6 mega electron volt for mass number 238. So here from 56 to 238 has a maximum value. Then next comes is the specific binding energy is lower for both light nuclei and heavy nuclei. Specific binding energy is lower for light as well as heavy nuclei, right? The next is sharp peaks of binding energy. You can see here sharp peaks of binding energy per nucleon ranging from 2 to 20, okay, up to here. This indicates these nuclei are relatively more stable than other nuclei in their neighborhood. So from here up until here, that is from 2 to 20, nuclei are more stable than the other nuclei in their neighborhood. So these are the features of binding energy curve. Go through the textbook so that you can understand. It is very easy to understand. Just by reading you can understand this. Okay, students. And next is the conclusion. What conclusion we can get from the binding energy curve? The force is attractive and sufficiently strong to produce binding energy of few mega electron volt. We have seen, right, this. We have maximum value here. So it gives a conclusion that force is attractive and sufficiently strong to produce binding energy and strong enough to produce binding energy. Then binding energy in range from 30 to 170 is constant, indicating that nuclear force is short-ranged. Nuclear force is short-ranged. That is, we have already told binding energy per nucleon is independent of atomic number. That is, it is constant. From here to here it is constant, right? So this gives us a conclusion that nuclear force is short-ranged. So next is a heavy nucleus with the A is equal to 240 has lowest specific binding energy compared to the nucleus with mass number 120. So nucleus 8 which has a mass number has 240, it breaks into two, that is of mass number 120 nuclei. Nucleons get more tightly bound, therefore energy will be released in the process called nuclear fission. That is, this indicates that there undergoes a process known as nuclear fission. That is, what happens? See, once again I'll repeat this point. A heavy nucleus, that is with mass number 240, here represents that it breaks into two nuclei of mass number 120. This indicates that nucleons get tightly bound to each other, which therefore the energy will be released. That is, it undergoes a process known as nuclear fission. We will be seeing in the further videos about this. That is in our further classes. Okay, don't worry about this, but you need to note down the point. And next is, when two light nuclei ranging of about greater than or equal to 10 join to form heavier nuclei. So here it was splitting of nucleus. Here is a nucleus getting paired, join, or they will join to form heavier nucleus. Therefore, EB and fused heavier nuclei. Fused means they are getting combining. That is, they are combining, joining together to form a heavy nucleus. So energy, in this case, energy would be released in the process, and that process is known as nuclear fusion. Okay. So what conclusion we have got from this binding energy curve? One is the force is attractive and it is sufficiently strong to produce binding energy. We have seen here, right? We got this much of energy for this and this much of energy for this. Therefore, force is attractive and it is enough to produce binding energy. That is, binding energy gives what? Specific binding energy gives the stability of the atoms, right? Now, next is the nuclear force. It's short-ranged. How we can say? We have seen a binding energy per nucleon is independent of atomic number. That is, it is constant up to some point. Therefore, that is from here to here it is constant. This shows that nuclear forces are short-ranged. Next, a heavy nucleus that is with atomic mass number 240. It is splitted to two other elements, that is with the mass number 120. This shows us there undergoes a process known as nuclear fission. We will be studying in our next class. And next is when two light nuclei, here it is splitting, here they combine to form a heavy nucleus. So light nuclei combines to form heavy nuclei. Therefore, there undergoes a process known as nuclear fission. That is, energy is released in the process when light nuclei combine to form heavy nuclei. Now, let's move on with the nuclear force. The force which binds the nucleons inside the nucleus is nothing but nuclear force. Force which binds means binds the nucleons. Binds the nucleons, holds the nucleons in the nucleus are the nuclear force. Now let us see some of the characteristic features of nuclear force. That is, characteristics of nuclear force. Nuclear force is the strongest known force in nature. It is a strongest force in nature. Next is nuclear force are short range forces. We have seen through the binding energy curve, right? Nuclear force are short range force. Then nuclear forces are charge independent. They are charge independent. Why? The magnitude of nuclear force is same between two neutrons or a proton and a neutron. Therefore, they are charge independent. Then comes nuclear forces are spin dependent. Spin dependent, I think you have heard this in your chemistry about spin. Quantum numbers, spin, you have seen in your chemistry. So, the nuclear forces are spin dependent because force of attraction between two nucleons having parallel spin is stronger than force between two nucleons having anti-parallel spin. So just try to understand the characteristics. Just characteristics is important. The other things you will learn in your chemistry class. Okay, no need to worry too much for this. Next is they have the property of saturation. They have the property of saturation. That is, the nucleons in the nucleus can interact only with its neighboring nucleus. Only neighboring nucleus they can interact with. Therefore, they have the property of saturation. And the last is nuclear force are repulsive force. They have the repulsion property. When the distance between the nucleons is very close, that is nearly equal to 0.5 femtometer or Fermi. So this is about nuclear force. Nuclear force is nothing but the force which binds the nucleons in the nucleus. And some of the characteristics of nuclear forces are, it is the strongest force known in the nature. Nuclear force are short range force, we have seen in the curve. Charge, it is a charge independent because magnitude of nuclear force is same between two neutrons or protons and a neutron. And next comes is it is spin dependent. You have seen about the spin in your chemistry. So I think you know about spin. Therefore, nuclear force is spin dependent, means the force of attraction between two nucleons have parallel spin which is stronger than force between nucleons having anti-parallel spin. Next, they have the property of saturation, that is, they can only interact with a neighboring nucleus. Nuclear force are repulsive. When the distance between nucleons is very close, that is point Fermi, femtometer or Fermi, then they shows the repulsion between two nucleus. Thank you, students.